Hi. So thanks for inviting us to present. Basically, we'll follow a little bit what Sarah was mentioning, also with the previous talk, and the implication with regard to oil and gas exploration, but as well the implication for understanding paleoclimate and paleocean circulation with regard to plate tectonics. So this work is mainly on the Norwegian Sea and was done my time with AKBP, and I would like to thank them for sharing the result of this multi-year study on the Norwegian continental margin. So for the one who are not too familiar with the Norwegian continental shelf, we have three different areas. To the north, we have the Barents Sea, in the center, the Norwegian Sea, and in the south, we have the North Sea. As you see in the creaming curve, there is a lot of exploration in the North Sea with a lot of oil that has been discovered, followed by the Norwegian Sea and the Barents Sea. And at the moment, there is an effort to try to find more resources, especially in areas that are less explored, like the Barents Sea and the Norwegian Sea, and potentially in stratigraphic traps. So let's see if I put the pointer. Yeah. So this is in mid-Norway. So in mid-Norway, the main resources are being explored in the Jurassic Plain. But on the way down, when they were drilling in the early 80s, they start to realize they had a lot of Cretaceous sand throughout at different level, from Appian Albion all the way to the Maastrichtian, or like the boundary with the tertiary in the Paleocene. So we will focus only on the Cretaceous today. So here you can actually see the stratigraphic column where you have some long sand in the Albion, and then Cenomanian, Turonian, and then in the coniation you have the Lucene. So in this area, a lot of fields have been discovered, and some quite large discovery. So you have the Alfhild discovery in 2000, about 300 million barrels of oil recoverable, and about 50 to 60 kilometers long along the paleo slope. And then in other places, you have four-way closure, like the Ormelang field with almost 600 million barrels of oil equivalent. So through time, the exploration started in early 80s, 81 until now. So it's about 45 years of exploration. So there is a few wells drilled in the early 80s, and then they were visited and trying to understand the depositional environment, how would they distribute, what is the quality, and how we find stratigraphic traps. So Shannon came to Norway to describe a lot of the core along the Norwegian continental margin, and he started to notice there was some mass transport and then the effect of some bottom current. But afterward, a lot of the explanation for those Cretaceous sand were related to turbidite system filling in some of the rift morphology in the basins around, as you see in all those different cartoons all the way to 2021. So at the same time, after the discovery of the Hadfield field, which is this elongated amplitude, so this soft represent the gas field, and then there is sand throughout the area, and this is the contact about this point. If you go up dip, you have a lateral pinch out for about, as I said, 50 kilometers. So a lot of questions were, how do we form those stratigraphic traps, and what are the processes controlling this type of large stratigraphic traps? So there was a lot of work done with Stirling, the edge of the wedge, and trying to see the link between the paleotopography of the rift and the way the turbidite were deposited in the basin. But as you have seen now over the last few talks, there is a lot of discussion with regard to mixed system in deepwater system. And recently there was this sand detachment, maybe analog for stratigraphic traps, and then we have all the shallow marine system. But then when we get on top on the slope or in the basin floor, we have, of course, the turbidity system that has been quite successful in the past. And then there is some hints with the class 3, with the contrite deposition in the center of the basin, as Sarah mentioned now, with some of the cases in Mozambique or Tanzania. And then we also have the contour current erosion that could actually make the sand to be detached from the feeder system, like in the picture A here. So if we start to think about the model with gravity deposits developed by Exxon and other companies, we get to see those deepwater systems where you have the canyon, the channel lobe, and then the distal fan system. But with the work from Fernuslo, we start to see that there could be a full mix of spectrum of system with well-defined, we know the way where some of the coarser sand can actually be remobilized and form those dunes or sheets. And then in other places where you have muddy contrite drift controlling the paleobathymetry and the deposition of the turbulence. So with that in mind, we tried to explore the Norwegian continental shelf, but by getting a better perspective, by integrating a lot of data. Usually we see a lot of the core, and we try to, like Kevin mentioned, trying to find key criteria to differentiate turbidite or contrite. But the idea here was to make the full use of the seismic data that is available in Norway, with almost 3D data covering the entire shelf, and not only doing seismic stratigraphy, but looking at the seismic geomorphology. So we are very lucky to work in Norway. It's a fairly mature area, and there is a lot of 3D data. For example, this survey from TGS, which is the pure, it's about 45,000 square kilometers, extending 400 kilometers of the margin. So how do we target those very large cubes, and how can we actually tease the detail to help us making the connection from basin scale almost to core scale? So there's a traditional approach, mapping with Petrel, and then the use of PaleoScan and integration with geoteric. And then one of the main turning point is trying to look at modern and ancient analog that is also supported by the drifter, as we have seen with Sarah, and then later on Javier, who will be presenting some of their work. This is very inspiring, trying to better get a picture of the complexity of those deepwater systems. So we will go through 3 cases, one in the Vestfjorden Basin in the north of the mid-Norway, one in the Donna Terrace, and one in the Møre. So we will start with the Lange, Lysing, and then up into the Maastrichtian with the Springer formation. So in the Vestfjorden, this was one of the first wells that was drilled in the early 80s, and you can see not many wells on the Donna and Alten Terrace. And there, Shannon Graham started to realize there was some event associated with bottom current and interaction with mass transport. So this is located in the north here, and here you have the base Cretaceous. Just to give an idea, you have a series of highs with the Gröna High, the Röda High, Sör High, and then you have some ridges outboard, like the Sklina ridges, and all those amplitudes here are related to those Cretaceous system, where in some places you see the canyon, and then you find all those interesting morphology down here. We will dive into more detail. So in the northern part, you have the Gröna High, and then you can actually map a lot of the canyons coming down, and then you have the basin. And here you can actually map the base of the BCU, which is represented on the map, and then the full Cretaceous sequence, where you see all those overlapping packages, and in some places thickening towards the slope. In that case, they drilled a well, they found a lot of sand throughout the Tertiary and the Cretaceous. They were deposited as, or interpreted as turbidity fan. So now if we start to link what we can see in seismic geomorphology with the well and the core, so in this case, the well is located up here, and then we start to see that we have the active canyons in red, and then some of the canyons were not providing a lot of sediment, but the southern one, and then you can actually map those deep water systems going to the north east into the basin. But we also see those sort of elongated systems. But when we look in the core, we find all those conglomerates and then those massive, mainly turbiditic system. If we go up into the level just above, we start to see that there is a new canyon that is being activated, and we see all those very nice channel system coming out and then being deposited into the basin. But then in this area of the well 3-1, we start to see all those elongated. And here we see a big difference with the sedimentary facies. We see all those cross-bedded, glauconitic, highly biotubated system, and a repetition of those. Those have been interpreted to be either low-density turbidite or reworked by bottom current. If we go to the interval just above, in the coniation, then we don't see any of the gravity processes coming down into the basin. We see all those along slope systems. So we have an evolution from downslope in the lower part of the Cretaceous and then up in the stratigraphic sequence with more along slope processes. Now, if we move to the Donut Terrace, just to the south, there was the Alfhild discovery, which is this elongated field with a stratigraphic pinch out towards the edge of the Newland Ridge. And then at the time, they had little patches of seismic and trying to do this seismic geomorphology connecting to the core. And then other models were showing axial and system coming down into the basin. But throughout those studies, there is always something that is coming back, is the presence of those enigmatic facies. And those enigmatic facies have been published in a lot of different period of time. So Shanungham in '94 were describing those as tidally influenced deposit, maybe estuarine with those crossbeds. Later on, they were interpreted as traction currents. And then recently, they were interpreted as either upper delta front or cross-stratified with the channel lobe transition. So we see we have a full spectrum of deposits, and as Kevin mentioned, sometimes it can be challenging to find out the deposition element from just the core. So let's see how we can actually do this with the help of seismic data. But before we move on, it's quite important to understand the processes, because all those cross stratified sandstone, if you actually look at the reservoir property, they're usually above 1 Darcy, and in some places up to 40 Darcys. And then the facies 2, L2 here, you see all this dewatering, and then those are massive sand with dewatered. You have the same range of porosity, but the permeability are a lot lower. And then the same when you get down into those rippled and laminated sandstones. So how can we actually predict and link what we see in the core with what we see in the seismic? So when it comes to seismic, there's been a lot of improvement in the Norwegian Sea from, if you look at data before 2007 to data after 2017, you start to see a lot more definition in the Cretaceous. And then you start to see the field here with the pinch out here, and then you see those little blips of amplitude appear. So if we start to look at the level of the Alfhild field, where there is this discovery with about 300 million barrels of oil equivalent, which is mainly gas and condensate, you start to see the pinch out, and then you see the response on the gas. But then in other places, we start to see some features. And if we go to the next slide, when you actually do the detailed seismic interpretation, you start to see all those elongated ribbons or furrows. So this is something interesting at the level, but maybe the seismic quality or the thickness of the sound doesn't allow us to see any geomorphology in this area. So let's move just one slice below. And then if we take the one just below, now we are in the Lange formation, which is just lithology definition. But we get to see that we have some features appear, which are those on the pin chart. We have those elongated anomalies, and then they are drilled in some places, and we know that we have sand, so there could be elongated dunes, a little bit what we found in the Oligocene system in Brazil with the work from Petrobras and by Muti in 2014. And then in other places in the basin down here, we get to see some of those crescent shape, maybe Barken dune encased in mudstone. So we are lucky in that case is that we have maybe thin sands and encased in mudstone with a little bit of gas, and it allows us to see this seismic geomorphology. Then if we move further south, we can go into the Möhre Basin with the Froan Basin, and this is the Ormelange field. So the Ormelange field is this very thick package of sand. So to do that, again, is to always good to make the full use of the 3D data available. In this image, you have a surface almost extending 250 kilometers. Here, outlined in dashed white, you have the Ormelange field, but we will focus mainly on the edge of the basin here, in this Upper Cretaceous Paleocene elongated mound on the edge of the Froan Basin. But if you look here, you have something very similar up here. So when we look at the seismic line in the area up here, you can actually start to see this little blip or this little mound on the seismic data at the transition between the Upper Cretaceous to Lower Paleocene. So if we make some section throughout, so if we take a section along the dip, you start to see this mounded sort of geometry and pinching out as you go south. And then you start to see this erosional moat potentially in the area. If we take one along the axis of the system, you start to see all those shingles downlapping and then pinching out as you go to the north. And this is about 45 kilometers from this end all the way to the tail end of this mounded features. And we don't have much time now, and the seismic quality is not good enough, but we can actually start to notice all those deep water channel system coming down the slope here. So if we start to map in detail, we can actually see a lot of different units. So we have the unit 1, which is this channel system with those finger-like features. Then you have the unit 2, which is the elongated one that goes about 45 kilometers. And then you start to form this unit 3, and you see the orientation of this mounded feature is slightly changing. One of the things to notice on this RGB blend is that we have this highly polygonal faulted interval. And then when we go towards these mounded features, we lose the polygonal faults, and then the frequency content is changing, most likely associated with lithology. And right on the edge, you start to see those zebra type features, and maybe here some elongated features. So if we do a zoom in and we look into this part, we start to see a lot of, on this seismic inset, a lot of scours formed, and those scours have this almost north-south orientation. And then as you go to the north, you start to see those dune forming, which what we see on the spectral decomposition RGB blend appear. And then the polygonal faults. if we look now on those zebra features, we can interpret them as sort of sediment waves along the basin. And then by using different attributes from the proximal to distal, we can actually see they are elongated along the axis of the very large drift. So when we look at the concept, a little bit what Sarah was mentioning with proximal to distal with regard to the contourized system, a long slope process, and proximal to distal with regard to the turbidites, we start to look at all those different features with the polygonal fold, the sediment waves, the mounded, elongated features, the dunes, and the scours. So we start to see the effect of bottom current modifying the turbiditic system coming down into the basin. So one of the things that we have noticed is that revisiting all this data and history of exploration in the basin, but with the use of the 3D seismic data that allows us to actually dive into the detail, allowed us to get a better picture of what's happening at the basin scale, but also how it's helping us to understand the reservoir property, the mechanism for forming stratigraphic traps into the basin. And this has implication for future exploration, either opening new ideas and developing new play concept in a relatively mature shelf. It can also help us to bring additional smaller interval into production very close to infrastructure. And then with regard to production, allowing us to better understand the 4D response and drilling infill wells and so on. So this is the main application here that I presented is for oil and gas exploration, but then there is a lot more implication with regard to paleocean circulation, paleo-basin morphology, and also the different water masses in response to opening and closing of the North Atlantic and the Norwegian Seaway. So with that, I would like to thank again AKBP for allowing me to present some of those images and part of this multi-year regional studies, and also TGS for permission to display some of the seismic line from the multi-client seismic, and Vår Energy for supporting my participation at the forum. Thank you.